The Global Positioning System coordinates everything from commercial airline routes to the mapping app on your phone. But that entire network breaks down if the internal clocks on its satellites drift by even a fraction of a nanosecond. In physics, measuring things correctly is what makes the modern world function. To measure anything, we start with three core SI base quantities: length in meters, time in seconds, and mass in kilograms. These are the fundamental building blocks for describing the physical universe. This table shows how we handle the extreme extremes of those quantities. Because the universe scales from the mass of a proton to the width of a galaxy, we use scientific notation and prefixes like giga or micro to scale these base units efficiently. This brings us to a baseline rule. Before you solve a single equation in physics, you have to translate your raw numbers into correct, scalable units. We do that translating through a method called chain link conversion. Because 1 minute equals 60 seconds, dividing one by the other creates a ratio that equals exactly 1. You can write it as 1 minute over 60 seconds or 60 seconds over 1 minute. Multiplying by this ratio changes your units without changing the actual physical amount. If we want to convert 2 minutes into seconds, we set up an equation using the ratio that puts seconds on top. The core rule here is to treat your units exactly like algebraic variables. The minutes on top cancel out diagonally with the minutes on the bottom, leaving you with 120 seconds. This creates a built-in self-check. If your unwanted units do not visually cross out diagonally top to bottom, your fraction is upside down. Flip it and try again. A calculator might output a number with 7 decimal places, but that creates an illusion of false precision. If you measured a plank of wood with a basic hardware store ruler, your raw data simply isn't that accurate. To avoid over-reporting, you must count your significant figures. If your initial measurement only had 3 significant figures, you must round your final answer to exactly match that limit. Notice that decimal places and significant figures are not the same thing. Shifting the decimal point to change units from millimeters to meters adds zeros, but all 3 of these numbers still contain exactly 3 significant figures. Let's test this. Pause the video and try converting 1 kilometer into micrometers. Output your final result in scientific notation, maintaining 2 significant figures. Here is the correct setup. You convert kilometers to meters and then meters to micrometers. The unwanted units cancel diagonally, leaving an answer of 1.0 times 10 to the 9th micrometers. Significant figures dictate the honest limits of a reported measurement. They override whatever intermediate decimal places pop up on your screen along the way. Looking at sample problem 1.01 from the text, we face a different challenge. Sometimes exact numbers are impossible to find. In these cases, we rely on order of magnitude estimates, rounding to the nearest power of 10. To find the length of string inside a massive, tangled ball, we first simplify the messy real-world object into a perfect sphere. By assuming pi is roughly 3, the volume formula easily simplifies to 4r cubed. Next, we define the volume of the string itself. If we view the string as a long cylinder with a cross-sectional area of d squared and a length of L, its volume is d squared times L. Because the volume of the string must equal the volume of the sphere it creates, we set the 2 equations equal to each other. Now we can easily isolate our unknown variable, length. Granting yourself permission to estimate shapes and simplify constants is a critical tool. It allows you to quickly verify if a theoretical answer is physically reasonable before doing the granular math. This section of the text introduces density. Calculating it requires combining everything we've just covered: unit consistency, algebra, and precision limits. Using the variables from sample problem 1.02, we set up our density calculation by dropping our raw mass and volume measurements directly into the equation. Dividing these yields an initial output with a long trail of decimal places. But checking our input variables, we see they are limited to 2 significant figures. We apply that rule, trimming the decimals and arriving at a proper, honest answer of 1.4 times 10 to the 3rd kilograms per cubic meter. This leaves us with 3 core grammar rules for physics. 1. Define your SI base units. 2. Verify conversions with diagonal cancellation. 3. Let your least precise input dictate your significant figures. Mastering these measurement rules is the mandatory first step. Once you trust the baseline numbers, you can confidently tackle the complex physics formulas built on top of them.